Here we'll introduce the triangle inequality and then use it to explore some satellite data. But first, which of these polygons is a triangle? Right, this is a triangle with 3 sides. Let's take a closer look. Suppose I tell you that this side has a length of 8 and this side has a length of 11. Then how long would you say this third side is? Great, so it turns out this side has a length of 13. Now the question we'll be asking is this. If you know that 2 sides of a triangle have lengths of 8 and 11, what's the longest that the third side can be? Well, if we stretch out these 2 sides, we can make the third side between these points longer and longer. And now we've fully stretched out these 2 sides, and we don't even have a triangle anymore. We have a line segment. There's no way we could stretch these sides to make our third side any longer. So the third side of our triangle must be less than the length of this entire line segment, which is how long exactly? Right, the third side must be less than 19. If its length is 19, like this, then you don't have a triangle at all. You have a line segment. To make a triangle, we have to bend this a little bit. And you can see that the third side will be less than 19, which is the sum of the other 2 sides. And that's the triangle inequality. For every triangle, each side is always less than the sum of the other 2 sides. Let's see some more examples. Suppose these are 2 side lengths and we have a third side that's greater than the sum of the other 2. Can we make a triangle with these 3 side lengths? Well, when we try assembling them into a triangle, it doesn't work. Even if we stretch out the 2 shorter sides as much as we can, we still don't get a triangle. Next, let's see what happens if the longest side exactly equals the sum of the other 2 sides. If we try assembling these into a triangle, we still run into trouble. If we stretch out the 2 shorter sides as much as we can, we get a line segment which is not a triangle. Finally, let's look at when our third side is indeed less than the sum of the other 2 sides. Sure enough, we can make a triangle with these 3 side lengths. So again, for every triangle, each side must be less than the sum of the other 2 sides. Next, suppose 2 sides of a triangle have lengths of 7 and 12. Here's a possible length for the third side, since each side is less than the sum of the other 2 sides. But if we try making this third side a little shorter, now our side of length 12 equals the sum of the other 2 sides, and you can't make a triangle with these 3 lengths. So if 2 side lengths of a triangle are 7 and 12, then the third side length must be greater than what value? Right, this third side must be greater than 5. So here's a side length that's a little more than 5, and sure enough we can make a triangle out of these 3 line segments. So given a triangle with side lengths A, B, and C, which of these statements here must be true? Is A definitely less than B plus C? Is B less than A plus C? And is C less than A plus B? Precisely, all 3 of these must be true. So these 3 inequalities are another way to write the triangle inequality. Each side, A, B, and C, must be less than the sum of the other 2 sides. Now with this interactive, you can check the triangle inequality for yourself. Make any triangle you want by dragging around these 3 vertices. Up here, you can see that for every triangle you draw, each side is always less than the sum of the other 2 sides. And when you violate the triangle inequality, so you have something other than a less than symbol up here, that means you no longer have a triangle down here. You have a line segment instead. So after you've played around a bit, try answering this question. If 2 sides of a triangle have lengths of 13 and 9, which of these choices are possible lengths for the third side? Excellent! Next, take a look at these numbers here. Which of these are possible side lengths for triangles? So for example, could the 3 sides of a triangle have lengths of 4, 5, and 7? What about 4, 4, and 9? For your final challenge, suppose you work for an agency that launched 3 satellites into orbit around the Earth. Your satellites are able to position themselves automatically, and they report back to you the distances between each pair of them. On Monday, here are the distances they report, and on Tuesday, they report these distances. The data from one of these days is far more believable than the other. Which day would you believe is correct? Excellent work! Together, these 3 satellites form a triangle, and the lengths of this triangle's sides, meaning the distances between the satellites, must obey the triangle inequality. According to Monday's data, adding the 2 shorter sides, 32,000 and 41,000, gives you 73,000, but the third side, 75,000, is greater than the sum of the other 2. So you can't make a triangle out of these 3 distances, but you can make a triangle using Tuesday's data, so these numbers are believable. So whenever you have 3 lengths, the triangle inequality tells you whether or not they can be the lengths for a triangle's 3 sides. In short, each side must be less than the sum of the other 2 sides. Here's a triangle, and let's color its 3 angles. First off, which is the largest angle in this triangle? Exactly, this blue angle down here is the largest of the 3. Next, which of this triangle's 3 sides is the longest? Well done, so it's this side up here. So the longest side is opposite from the largest angle. That's pretty interesting. Next, which of these angles is the smallest? Yeah, so this red angle is the smallest of the 3. And which side would you say is the shortest? Precisely, so this side is the shortest. In general, for every triangle, the shortest side is always opposite from the smallest angle. And as you already saw, the longest side is always opposite from the largest angle. And what about the middle side, whose length is somewhere between the shortest and the longest? It's opposite from the middle angle, whose measure is somewhere between the smallest and largest angles. So at this point, do you want to work through a proof of these ideas, or would you rather just skip ahead? Okay, so now let's try a few sample problems. With this interactive, you can make any triangle you want by dragging around the 3 yellow vertices. Now each angle and its opposite side have matching colors, and you can see all their lengths and measures up here. Sure enough, the largest angle and longest side go together, and the smallest angle and shortest side also go together. Try making different triangles to prove to yourself that this is always true. Then, when you're ready, give this question a shot. In an obtuse triangle, meaning a triangle with an obtuse angle, the side opposite from the obtuse angle must be what? The shortest side? The longest side? Or could it be either one? Excellent! So in an obtuse triangle, like this one, the obtuse angle is always the largest angle. So that means its opposite side must be the longest side. Okay, so next, give this question a shot. Which of these could be the measure of the angle that's opposite from the shortest side in a triangle? This is a tricky question, so feel free to ask for a hint if you need it. You've done some excellent work here. So just to recap, the shortest side of a triangle is opposite from the smallest angle, and the longest side is opposite from the largest angle. And of course, this means that the middle side is opposite from the middle angle.